All right, hello. Welcome back. We're going to be talking about two different topics today. So we are still in Unit 2, Molecular and Ionic Compound Structure and Properties. I'm lumping together Topic 3 and Topic 4 for a couple of reasons. First of all, we've already talked a bit about ionic solids, so there isn't a ton of new info here. And then also Topic 4, Metals and Alloys. This stuff just isn't really all that difficult. So there's not a ton of new stuff for us to cover, and it's not really anything super challenging. So I think it's totally fine to lump these two topics together, at least for the video. Here are the learning objectives from the course and exam description. I'm going to let you read these on your own if you want to. I don't want to waste any time going into this too in depth. Let's just dive into what we're going to go over today. Okay, so we're going to talk about solids. Okay, both metals and ionic solids. We're also going to talk about these things called unit cells, and we're going to use unit cells later in the problem-solving video to calculate density of substances. Okay, so there will be a separate problem-solving video that will come after this video. So like I said, we're going to get into how metals are structured and what goes on in a solid metal metallic bonding. We're going to talk about alloys, a word you might remember from last year, and then we're going to wrap some things up with just sort of a review of what we had learned last time with ionic solids. Okay, so a common theme throughout pretty much all of science, okay, whether it be biology, chemistry, physics, whatever, is the relationship between structure and properties, or structure and function. Okay, the structure of matter, what it's made of, fundamentally determines its properties, or how it behaves. Okay, and that is one of the big ideas that we as teachers and instructors and professors try to impress upon students. Okay, so today we're going to be looking at solids, and in particular we're going to be looking at how the structure of the matter that makes up a solid, how that structure then gives rise to the properties that those solids have or exhibit. Okay, so a little bit of sort of basic information about solids in general. Solids can generally be classified into one of two categories. Crystalline solids, which have a highly regular arrangement of their components. This does not necessarily mean a crystal like a gemstone or anything like that. In fact, most solids are crystalline solids, okay, as we'll see. Amorphous solids have considerable amounts of disorder in their structure, okay. These are not nearly as common. In class, if you are interested, I can tell you more about some select examples of amorphous solids. But like I said before, crystalline solids are much more common, and so they're going to be our main focus for our discussion today. The components in crystalline solids, which are typically atoms, ions, or occasionally molecules, are usually represented by lattices, okay, or crystal structures, and you should remember us talking about that from 2 videos ago. The smallest repeating unit of a lattice, right, which is then repeated over and over again, right, the highly regular arrangement, the smallest repeating unit of a lattice is referred to as a unit cell. Here are some unit cells. They can be depicted in a number of different ways. So the unit cell itself is the smallest repeating unit, right? The lattice pictured here is like multiple of the unit cells put together. In fact, if you look closely, it appears to me as if the lattice that they've drawn here is made up of 8 different unit cells put together, right? There's like one here, and then one here, and then one here, and one here. So like 4 on top, and then 4 on bottom. Okay, and that would be the same for these other different crystal structures. Okay, now I will bring us back to the course and exam description. It does say here, right, knowledge of specific types of crystal structures will not be assessed on the AP exam. Okay, Study of specific crystal structures is not essential to an understanding of the big ideas. So it's not important or necessary that you memorize any of this information. Okay, simple cubic versus body-centered cubic versus face-centered cubic. That is not important. What we are going to do, though, is we are going to do some calculations with these reference pictures available to us, and we do need to just sort of understand how solids behave in this like lattice formation. Okay, so this table can be found in your book on page 394 if you'd like to take a better look at it. I'd recommend taking a look at it. See if you can understand how the unit cell here results in this space-filling unit cell picture. Okay, notice how a lot of these spheres have been cut into, well, not entire spheres, right? The one example I'll show you here is look at the difference between simple cubic and body-centered cubic. The only difference in the unit cell is that in the body-centered cubic unit cell, there is this sphere here in the center, so like an atom, right, in the center. Whereas the simple cubic does not have that. So like the lattice for a simple cubic cell is very simple, right? It's just literally the same atom repeating over and over again, and they're all at like 90-degree angles to each other, right? Whereas here, that is not what we have, right? There's an atom in the middle of that cube in each of those cubes, right? And so you can see how that manifests itself in the space-filling unit cells, right? Here, we just have like 1/8 of a sphere on each of the corners, right? We have the same thing here, but we also have that entire complete sphere in the middle, okay? And so we're going to be doing some analysis and some calculations of these different unit cells to calculate things like density, okay? And that's what we're going to do in the problem-solving portion of the video. Okay, so let's go ahead and talk about metals. We haven't talked about metals before, not in great detail, I should say. Metals are often found in pure solid forms in nature, not always like big chunks of them, but you can find them in pure like solid elemental forms. This is in contrast to nonmetals, okay, which are usually found in compounds or as like gases, for example, right? So a lot of times nonmetals will be found in compounds, think hydrogen and oxygen in water, right? Or as pure gases, like oxygen gas or nitrogen gas or the noble gases, right? So what we're going to talk about today is metals and specifically how solid metals exist, like what's the structure there, what's going on. So it's called metallic bonding. It's different than ionic or covalent bonding. It's just its own sort of category. I'll be honest with you, I don't know that much about metallic bonding. I've never really had to know that much other than the few little details that I'm going to give you here. So, models of metallic bonding contain a crystalline arrangement of cations, okay? So, metals are almost always arranged in some sort of regular structure, like you can see here. Okay, this is obviously just two-dimensional, but there you go. Okay, so there it's a crystalline arrangement of cations in a sea of electrons. Okay, and then this is sometimes referred to as the electron sea model. So once again, the details here are, I don't think, super important. It's one of those things that you just kind of need to know or to memorize, as it were. This is generally the model that we use to describe how metals exist in solid form. Okay, it's a regular crystalline structure of metal cations, positively charged ions, surrounded by their electrons that are sort of free to move around a bit. This model accounts for the properties that we observe in most metals: high malleability and ductility. Basically, those terms mean that metals are relatively easily, their changes can, their shapes can be relatively easily changed. So you can like press on them to like flatten them out. Think of like aluminum foil, right? And you can also like stretch them into things like thin wires, right? Most, like all wires really, are made of metals, right, with a few exceptions. This also accounts for a few other properties that we observe in metals, and that is that they are universally efficient conductors of heat and electricity, particularly electricity, right? Electricity is just the flow of electrons. So in this model, where we have the cations that are sort of fixed in place, but the electrons which are not, a flow of electrons is easy to maintain and establish because these electrons are not necessarily associated with any one atom or any one cation. So electrons can flow easily. That's why metals are used for wires, right, to conduct electricity. Okay, so I have one other slide here on metallic bonding. Once again, I don't think this information is particularly like mandatory for you to be able to know and explain, especially on the AP exam, but I think it's interesting. Many common metals that are used in technology are used for those properties that we just talked about. And a lot of times they are transition metals, okay? Like oftentimes they are transition metals. Let's look at a couple of these. So we have iron, nickel, copper, zinc, palladium, silver, tungsten, platinum, gold, mercury, etc. Okay, so the ones that I've highlighted here are the transition metals. These elements are metals due to their electron configuration, okay? So these metals only have 2 valence electrons. That's why you saw here these 2+ cations, right? So what this model is essentially saying, right, is that the metal atoms are like losing their 2 valence electrons to form this sort of sea of electrons, but they're still sort of satisfied by the d orbital electrons that they have. Remember, transition metals are their final electrons are in the d orbital. Once again, I'm not telling you this because I think you're going to have to regurgitate or discuss this on the AP exam. I just think it's a little bit interesting that all of these common metals that really do get used in industry and in technology are all transition metals. These elements over here are also metals, okay, as well as a number of these elements here, but they're not as commonly used as these transition metals are, okay? Okay, next thing to talk about is alloys. Okay, this is a word you may remember from last year, especially if you had me in class. Alloys are homogeneous mixtures of metals, and there are 2 different types of alloys. Okay, there are substitutional alloys, which consist of a host metal lattice, and one or more other metals that are of similar size that substitute into the lattice, composing what eventually is a mixture, right? The other type is called an interstitial alloy. This consists of, once again, like a host metal that has much smaller elements, usually nonmetals, that are placed in the interstices or holes between the metal atoms in the lattice. So rather than replacing the host metal like a substitutional alloy, these little smaller elements, particularly like carbon and nitrogen, or even smaller things like boron, they can come in and position themselves in the holes between the host metal atoms in the lattice. I've got some diagrams here that I'll show you. So first of all, substitutional alloys, they're not always composed of only 2 metals. I know that the drawings here are of 2 different metals, like 14 karat gold is composed of gold atoms with some silver. But there are some other examples here. So like, once again, brass is one that actually is just 2 metals. It's about 2/3 copper, 1/3 zinc. Sterling silver is made of silver and copper. But then you can have other alloys, substitutional alloys, which are composed of lots of different things. So here we've got pewter, which is made of tin, copper, bismuth, and antimony. Okay, and alloys are used because when substitutional alloys can just have different properties than the pure metals themselves. So sometimes those properties are useful, and so sometimes they are used for those useful different properties that they have. Okay, interstitial alloys, I think, are more interesting. They require much smaller elements, like I said before, usually non-metals, to fill the interstices or the holes between metals in the lattice. Okay, metal atoms in the lattice. So as you can see here, this is by far the most common interstitial alloy. It's referred to as steel. Okay, steel is not an element, right? Iron is an element. Steel is made of iron with carbon atoms in the interstices. Okay, and actually you can sort of increase and decrease the amount of carbon in steel to end up with slightly different properties in the steel. I don't remember off the top of my head exactly, what those different properties are. I know that sometimes if you want like much stronger steel, you need to have more carbon, for example, something like that. Anyways, how it really works though is interesting. Okay, the carbon atoms present in the interstices strengthens the lattice. Okay, so imagine if the carbon atoms weren't there, and you were like sort of taking your hand and sort of pressing on that cube of iron there, due to the sort of delocalized nature of metallic bonding, okay, with this sea of electrons, metal tends to be pretty easy to like reshape and reform, right? It's malleable and ductile. Adding the carbon atoms tends to make that more difficult. You can't change the shape of steel as easily as you can of just pure iron. Okay, so that's how this works. That's sort of the reason that we use steel. Okay, is for that purpose. And one other note. Okay, alloys can be both substitutional and interstitial. Okay, so you can have like this diagram down here where you've got these little green carbon atoms in between the irons. Well, you could also have some of those irons replaced by something else. Okay, so like stainless steel is an example of a both substitutional and interstitial alloy, with the base metal being iron, got some carbon in there interstitially, and then things like nickel and chromium that are substitutional components of the alloy. Okay, all right, so that's really it in terms of metals. Once again, the only sorts of problems that we're really going to solve with metals are going to be looking at these different cubic, these different crystal structures, these different unit cells, I should say, and we're going to be doing some calculations with density, okay? All right, and then the final part for today, I just wanted to sort of review with you guys some of the things we learned about ionic solids, okay, and ionic compounds. So, ionic compounds, they tend to be solids as well. Remember, that's sort of the theme for today, right? Solids. They are almost universally solid. Actually, it might be universally solid, like 100%, at room temperature, okay? And that is because there are very strong electrostatic attractive forces between the positively charged cations and the negatively charged anions in these ionic compounds. Okay, so like the cations and the anions are really strongly bound to each other, and so they usually adopt a solid form rather than liquid or gas where the ions would have to like separate, right? So they have extraordinarily high melting and boiling points. We're going to get into more of that in the next unit when we talk about intermolecular forces. Okay, so we'll visit this sort of concept again. So yeah, similarly to metals, ionic solids exist in crystalline forms, so regular repeating patterns. One notable difference, however, is that ionic compounds are made of at least two different ions or two different elements, right? Whereas metals can be pure. So the resulting crystal structures, depending on a variety of different factors, can be similar or different from the crystal structures found in pure metals. It depends on the size of the ions, right? If you have very large and very small ions, that can sort of alter the crystal structure. The ratio of ions. If it's a 1-to-1 ratio, then it may look a bit more like a metal. If it's a 1-to-4 ratio, then you might end up with a completely different looking crystal structure. Okay, just remember, right, that the details of those crystal structures are not something you have to sort of memorize. We just want to be able to use the models and talk about them in an educated way. Okay. All right, so here are a couple of those models. Really what I need you to know about ionic solids is this. Okay. Ions in an ionic solid arrange themselves in a way that minimizes their distance to oppositely charged ions. Okay, so anions and cations want to be as close as possible, right? While maximizing their distance to similarly charged ions. So anions and anions want to be far apart, right? Because they have similar charge. Okay, so as long as you understand that concept, that is going to be good enough, okay, for us. And just once again, remember that these arrangements here that we're looking at result in the lowest overall electrostatic potential energy for the system. Okay. Okay, and then I've copied 2 slides from the previous topic from 2.2. I just wanted to bring this up a little bit again, just in case you didn't have a good understanding of this before. So I was just talking about, how the ions arrange themselves, right? They want to be in what are called closest packed structures, okay? Whether that be something like this, referred to as like an octahedral structure, something like this, which is just a simple cubic structure, or something like this, which is a tetrahedral structure. Once again, remember the details there aren't important, but they are all closest packed structures depending on the size of the ion, the ratio, things like that. I wanted to talk a little bit more about how those sizes of ions and how the charges of ions can affect lattice energy. Okay, so I'm just going to mention this one more time and then the video will be done. Okay, so when you're looking at a closest packed structure, okay, ion size can strongly influence the lattice energy, or the amount of energy that's released when the ionic solid is formed. Okay, if you have large ions, okay, the distance between those ions is going to be larger. Okay, which means R or D, whichever variable you want to use, like the distance between the ions is going to be bigger. That means the lattice energy is going to be smaller. The positive and negative ion can't get as close to each other as they might like due to their size, and so it's not as favorable if the ions are large, right? So that's what this says here, right? If R increases, then the lattice energy decreases, right? It's less exothermic or less favorable. And the flip side is true, okay? If the ions are very small, they can get closer together, and so that means that R is decreasing, right? And so that results in a more exothermic or more favorable energy. And then you can also talk about lattice energy in terms of ionic charge. So when you're talking about an ionic solid and you're trying to talk about lattice energy, the charges of the ions can matter as well, okay? So the bigger the charges, the more exothermic or more favorable the energy is going to be, okay? And if the charges are smaller, then the lattice energy is going to be lower or less exothermic or less favorable, okay? You actually had some homework problems that asked you about things like this. I think during class next time we're going to go over some of those problems, because this is a particularly important thing that I want to make sure that we cover really well, because you're practically guaranteed to see some questions about this on the AP exam, so I want to make sure that we hit this pretty well. Okay, I think that's it. Like I said, there will be a problem-solving video where we use those unit cells to calculate some densities, but other than that, that's it for these 2 topics. Okay, so it's, like I said, not a ton of content, not anything particularly that difficult, and so that's why I condensed them together there. All right, thanks for watching, and I'll see you in the next one.